This lesson is about solving systems of linear equations using the elimination method. We'll first revise solving a system of two equations with two variables, and then we'll expand the method to three equations and three variables. So there's a couple of different ways that we can proceed with this example. Essentially, in order to eliminate either x or y, we need to multiply one of the equations, or sometimes both of the equations, so that the coefficient of x or of y is the same, and then we can look at subtracting or adding the equations together. So we'll start by numbering the equations 1 and 2, and we're going to keep track of each process that we follow. If I want to eliminate x, I need the coefficients of x to be the same. So I'll start by multiplying equation 1 by 3. That gives me 3x plus 3y equals 33. And it's important to remember to multiply each term in the equation by the same constant. So we'll call this equation 3. And now we've got two equations, both with 3x in them, so we can subtract one equation from the other. I'm going to subtract equation 2 from equation 3, because that then leaves me with a positive coefficient of y. So 3x take 3x is 0, that's been eliminated. 3y take 2y is y, and 33 take 26 is 7. Now that I know the value of y, I can substitute that into one of the original equations. The easier one is x plus y is 11, so x is 4. So that's one way I could proceed. Alternatively, I could eliminate y, and that would mean doubling all of the terms in the first equation. 2x plus 2y is 22. I'll call that equation 4. And then if I subtract equation 4 from equation 2, 3x take 2x is x, 2y take 2y, that's been eliminated, and then 26 take 22 is 4, and again I can substitute that back into one of the original equations to give me the other value. So you'll see the solution is the same either way, but I suppose my advice would be try to keep the numbers as small as possible. So if you have a choice of multiplying by 3 or multiplying by 2, it's probably a good idea to multiply by 2, and it just keeps all of the numbers involved as small as possible. Now we're going to expand this method to solve a system of three equations with three unknowns, x, y and z. I'll start by numbering the equations 1, 2 and 3. And just as before, there are a couple of different operations that we can perform. We can multiply each term in the equation by the same constant, or we can add or subtract equations together. Essentially what we're trying to do is eliminate the same variable from two pairs of equations, and then we'll be left with two equations and two unknowns, and we can proceed as before. So there's no right or wrong moves here, it's just that some operations result in easier equations than others. So if we just look at equations 1 and 2 to start with, to eliminate one of the variables, I could multiply equation 1 by 2, and then I would have the same coefficient of x, or I could multiply equation 2 by 2, and that would result in the same coefficient of y, or I could multiply equation 2 by 3, and that would give me the same coefficient of z. But I'm going to start with that first option. So equation 1 multiplied by 2 is 2x plus 4y takes 6z equals 18. And I'll number that equation 4. So now I'm working with equation 4 and equation 2. I can eliminate the x's by subtracting one equation from the other. And if I look at the next term along, I've got 4y and negative y. So I'm going to do equation 4 take equation 2 so that I'm left with a positive coefficient of y rather than a negative coefficient of y. So 4y take negative y is 5y, and then negative 6z take z is take 7z, and then 18 take 0 is 18. So we'll number that equation 5. So that's still an equation with two unknowns in it. So what I'll do now is work with equation 1 and equation 3, and again eliminate the x's so that I have a second equation involving just y and z. So I'll take equation 1 and multiply by 3, which gives me 3x plus 6y take 9z equals 27. That's equation 6. And this time I've got 3x and negative 3x. So instead of subtracting the equations, I'm going to add them together to eliminate those x's. So this is equation 3 plus equation 6. Negative 3x plus 3x, that's eliminated. 4y plus 6y is 10y. Negative 2z plus negative 9z take 11z, and then 12 plus 27 is 39. So that's my equation 7. So you see now I have two equations with two unknowns, equation 5 and equation 7, so I can proceed just as before in the first example. I've got 5y and 10y, 7z and 11z. So the easiest thing that I can see is to multiply equation 5 by 2 to get 10y take 14z equals 36. So that's now equation 8. And then I've got 10y in both of these equations, so I'm going to subtract. And remember, I'm looking for positive coefficient of z, so I'm going to do negative 11z take negative 14z. That's equation 7 take equation 8. So negative 11 take negative 14 is 3z, and then 39 take 36 is 3. So that's equation 9. And this is a simple z equals 1. Now once I've got one of the unknowns solved, I know that z equals 1, I can now substitute back into some of the previous equations. So if I use equation 5, so substitute into equation 5, then I've got 5y take 7z, so that's 7 is 18, so 5y is 25 and y is 5. And then I can substitute back into one of the original equations. Let's substitute back into equation 1. So sub into equation 1. We've got x plus 2y, so plus 10. Take 3z equals 9. So x plus 10 is 12 and x is 2. There are three solutions: x equals 2, y equals 5 and z equals 1. And as I said at the beginning, there's more than one way that this could be done. These were the moves that seemed the easiest to me at the time. If you did it a different way but still managed to get these three values, then that's absolutely fine. But it is important that you keep track of your moves, firstly by numbering each equation, and secondly by writing down at the side if you're multiplying equations or adding or subtracting equations, or if you're using substitution. You need to show that you've used a systematic approach rather than just guessing or trial and error, luckily stumbling across these solutions.